Hello, calculus fans. All right, so now we're going to expand on our notion of moments and center of mass. Let's consider a flat plate. This is called a lamina. It has uniform mass density rho, so it's a sort of uniform thickness. Every square centimeter of this thing has the same mass. It's going to occupy some region in the plane. And what we want to do is locate the center of mass of this region. We're going to take advantage of a symmetry principle. If you have your region R is symmetric about a line, L, then the center of mass of R lies on L. A simple example, if you have a rectangle or a square or a circle, then the center of mass of that region lies right at the center of that thing. We're also going to define moments so that if the entire mass of a region is concentrated right at its center of mass, then the moments will remain unchanged. We also want moments to have an additive property, that if you have a region which is composed of two non-overlapping regions, then the sum of the moments of those individual regions is the moment of the entire region. Let's suppose that the region we're interested in is the region under the curve y equals f of x, above the x-axis, and between x equals a and x equals b. We'll divide the interval a to b into n subintervals using partition points x0 through xn. As usual, our subintervals are going to have equal width, delta x equals b minus a over n. Now this time we're specifically going to choose the sample point xk star to be the midpoint xk bar of the kth subinterval. So that is to say that xk bar is equal to x sub k minus 1 plus x sub k all over 2. So then on the kth subinterval we get a rectangular approximation to the region under the curve. This is very much like what we did with the midpoint rule, except we're doing something totally different with this approximation. Now the center of mass of the kth approximating rectangle, and that kth approximating rectangle we'll call r sub k, is its center, c sub k, which has coordinates xk bar 1/2 f of xk bar. What we want to do is look at a picture. Okay, so here you see we've got the region under the curve, and over here we're creating approximating rectangles. And what you should see is that on this particular rectangle that I've drawn, we have the center of the approximating rectangle. The x coordinate of the center is, we can pretty easily see that that's supposed to be xk bar, and then the y coordinate of the center is half of f of xk bar. So you want to go halfway up that rectangle to get the y coordinate of the center. All right, so this coordinate of the center is really very important. We're going to refer back to that. Now the area of this rectangle is f of xk bar times delta x. So to get mass, you have to multiply by the mass density. You take the area, multiply by mass density. Rho is the mass density. So this means that the moment of the rectangle K about the y-axis is the product of its mass and the distance from the center to the x-axis. So this is the moment about the y-axis. So we have the mass, and then the distance, well, it's the distance from the center to the y-axis. And that's just an x distance. It's the distance to the x coordinate of the center. If we add everything up and take a limit, we're going to get this integral. So the moment about the y-axis is the integral from a to b of rho x f of x dx. This turned into the x, this turned into the f of x, delta x of course turns into dx. Now in a similar way we can compute a moment about the x-axis. We do mass multiplied by distance, but now this time to measure the distance from that rectangle's center to the x-axis, we're going to do 1/2 f of xk bar. That's a y distance because we're measuring the distance to the x-axis. And again, add up, take a limit, and this time we get integral from a to b of rho times 1/2 f of x quantity squared. It's squared because we have an f of x and an f of x here. Now our lamina, in this case, has constant mass density, and the mass is just the product of its density and its area. So the mass is equal to rho times the area, which is just equal to rho times the integral from a to b of f of x dx. So we get some formulas for x bar and y bar. X bar is the moment about the y-axis divided by the mass, and we get these integral formulas. And rho is a constant, so it cancels out. So we get the integral from a to b of x f of x dx and the integral from a to b of f of x dx. Y bar, that's m sub x divided by m. We put our integral formulas in, so we have rho times the integral from a to b of 1/2 f of x squared dx all over rho times the integral from a to b of f of x dx. And the rho's cancel out. Now you might ask why we are even going to deal with the rho's if they're just going to cancel out. Well, one of the things we can always do later on is consider laminas where the mass density is not constant. So rho, instead of being a number, is a function, and then you would have to have it in the integral and compute it when you compute these integrals. You wouldn't be able to factor them out as numbers and divide. Okay, that's all for now.